Good morning everyone. I'm Uma Maheshwari, Assistant Professor, Department of Electronics and Communication Engineering. In this video lecture series, I'm going to explain about the natural ventilation of a generator room. The main task objective of this is where an engineering assessment of the exchange of the temperature in a passive cooled environment is required for the cooled environment. Cooled environment is mainly required for the generator room in order to keep hold of the things. Lower system was to be used in order to facilitate an airflow around a room containing an electrical generator. Then we'll have computational fluid dynamics. This computational fluid dynamics was used to ascertain whether the proposed design was capable of meeting an imposed operating constraints. This computational fluid dynamics model, which could solve for the velocities of the turbulent flow, and it determines the capabilities of the airflow to transfer the heat away from the generator, the capacity to consider various combinations of external flow conditions, air temperatures, and the generator temperature were also being required. Here, an example of a large-scale Lua deployment in the civil engineering is shown in this diagram. Now we'll see about the natural ventilation, where natural ventilation is the process of supplying and removing air from an indoor space without the use of the mechanical systems and is considered a significant engineering challenge in the industry. This natural ventilation is considered through two key mechanisms. One is wind driven and another one is buoyancy driven flows. Wind driven. This wind driven is nothing but it relies upon the differences between the indoor and the outdoor static pressures generating the resultant through flow. First, inside the building wall there will be the low static pressure, where the pressure, high pressure will come away from the external resource and it will enter into the building wall. Next, the schematics of airflow under the buoyancy driven mechanisms, where the building wall here consists of an warm air out and the warm air in, where this arises through differences in fluid density, which is typical due to an imposed temperature gradient, and it is a phenomenon where it is also called as the stack effect, where in stack is nothing but pull out pushing. This is push pull, we'll call it as stack operations. So when cold air in and the warm air out is called as the stack effect. The next one is computational fluid dynamics, where this model here will shows the computational dynamic model of the proposed building design with the implementation of the full wall system as shown here. We'll see about the computational fluid dynamics. Here the model was parameterized such that the pitch of the lower blades could be altered with respect to the inlet flow to ascertain the sensitivity to directional changes in the airflow. This CFD system utilized both wind and buoyancy driven mechanisms for the heat exchange. The flow was assigned to be the turbulent for the Reynolds number calculation, and so the K omega turbulent model was utilized. The geometry was meshed in full 3D using hexahedra cells with a mesh density of circa 2.1 million cells. Initial boundary conditions were computed and the simulation was conducted using an in-house high-performance server. This is the simulation results of the CFD process, where it demonstrates the cross-sectional slices for temperature and particle streamlines for the airflow velocity. Here the temperature glimp plot illustrating the dispersion of the heat to the outlet via wind and the buoyancy driven techniques. The conclusion is that buoyant effects on the wind-driven ventilation were shown to be the primary form of heat dispersion from the generator. The CFD simulation demonstrated the average wind speed, which was capable of passively cooling all the surfaces of the generator. Thank you.